Welcome back to Chapter 5. We're going to continue our discussion of thermochemistry, and in this part we're going to talk about states and state functions, although I'm not going to get into a lot of detail about that. We're going to talk about the first law of thermodynamics, and then we're going to talk about work and heat and how those make changes in the energy of a system. So I mentioned a little earlier, thermochemistry is part of thermodynamics, and thermodynamics is the study of interconverting the different types of heat and energy. And in order to study that, we're going to look at different types of systems. So we defined a system before as, and I showed you a picture of a beaker. And I said, this is the system, and then everything else outside of that are the surroundings. And so you can have different types of systems, such as an open system, which is what I drew here. You can exchange mass and energy with the surroundings from the system when it's open. When it's a closed system, you can transfer energy, like through energy transfer like heat, but not mass. The mass is going to stay the same. And then an isolated system doesn't exchange mass or energy with its system, and you can kind of think of that as being insulated. So in thermodynamics, we study changes in the state of a system, and there are different things that are considered states, like composition, energy, temperature, pressure, volume, things like that. Energy, pressure, volume, and temperature are said to be state functions. And basically what this means is that the properties are determined by what state the system is in, regardless of how you got to that state. Okay, that state or character of that system. Don't confuse that with gas, liquid, or solid. So just a little bit better picture than my little beaker here is in an open system, you have an open to the atmosphere here. You can exchange heat in and out, and water vapor could actually go out, evaporate or condense back in if you have an aqueous solution or water system. In a closed system, we're going to put the stopper on it so we can no longer release mass or add mass, but we can still do heat exchange. And you're doing that, you're conducting that through the glass container in this example. So like if you've ever heated something up that was made out of glass or ceramic or whatever, and you touch it, it feels hot. And if there's a reaction going on that produces heat, like in the case of an exothermic reaction, then you'll be able to feel that, and heat's actually being exchanged with the environment. And then in an isolated, we've got this stopper here where we can't exchange mass, but then we're isolating it from the rest of the universe so that it also cannot transfer heat with the surroundings. So the first law of thermodynamics is that you cannot create or destroy matter, or otherwise known as energy is conserved. Okay, that means you can't make more or less. So you will do that in the system, but it's going to exchange things with the surroundings so that the system plus the surroundings is always going to equal zero. So if you increase one, the other goes down, that kind of thing. Another way of saying that mathematically is the change in that system is going to be equal to the negative change of the surrounding. So if you increase one, you decrease the other. That's all that means. So the change in internal energy, and that's what the U is designating, is given by the change. Delta means change. Is going to be the final internal energy minus the initial internal energy. And remember, I told you it's hard to measure actual energy, and so we look at the changes, and the changes are typically proportional to the totals. Energy, we already said, is defined as the capacity to do work or to transfer heat. So when a system releases heat or absorbs heat, its internal energy changes. And if a system does work on its surroundings, or the surroundings do work on the system, then also the internal energy changes. And so mathematically, we write that as the change in internal energy of the system is equal to Q plus W, where Q is the heat and W is the work that you did with that system. Okay, and so one of the examples you're going to see over and over again in your book is like a piston, and it's a little easier to visualize. You know, if you do work with a piston, you're going to push down and then let up. Okay, and so that's one way of showing doing work with it. And then of course heat, it's easier to see because you're either increasing the temperature or you're decreasing the temperature. Neither of these is a state function, and as I said, we don't talk about state functions a whole lot, but just the fact that the energy is a state function. Okay, so there's no dependence on the path as to how you get from one to another. So there are sign conventions for heat and work. And so if you absorb heat from the surroundings to the system, then your heat is going to be positive. Okay, so you're adding it to that, so it's a plus. If you're releasing heat from the system to the environment or the surroundings, that's an exothermic reaction because heat is leaving. Your Q is going to be negative because it's decreasing inside the system. Same with work. If you do work on the system, it's going to be positive. If you do work by the system, then it's going to be negative because you're going down. You're using up some of that original energy that you had. So here's my piston that I was talking about as the example. All right. So if Q is less than 0, okay, so that means it's a negative number, okay, then it's going to be releasing heat. So the heat inside goes down, okay? If you perform work from the system, then it's going to be a negative, and because the amount of energy, or I should say U, due to work also is going to go down. That's why it has a negative number. And then conversely, if I add heat to the system, then it's going to increase the amount of heat that the system has. If I do work on the system by pushing with the cylinder, in this case the piston, then that is also going to increase the amount of energy due to work done on the system. All right, if you're not getting this, kind of go back and listen to this slide again because it's important that you grasp this. So how do we use this? And so these are really simple, but people tend to get really confused about it. Okay, so I always, when I have one of these and I'm calculating changes in internal energy designated as delta U, and typically this is going to be in joules, but sometimes they'll throw kilojoules in there just to kind of throw you off. So you got to remember to make the conversion because, you know, kilos is 1,000, right? So if you have kilojoules, it's 1,000 joules, etc. Okay, so I always draw my box. Okay, so I got my box. So that's my system. inside. And the system is going to absorb 188 joules. So if I'm absorbing, then that means I'm pushing it in there. So that's adding 188 joules to my system. Now I don't know what the energy was to begin with. Okay, I only know that I'm changing it. And so that makes the energy of the system go up 188 joules. And it does work, 141 joules of work on its surroundings. So I'm using the system to perform work outside the system. So that means that 141 joules are going to have to leave the system to go to the surroundings in order to do that. And so the overall change is delta U equals Q plus W. Okay, so the delta U is going to be the heat, and it's a positive because I was adding it, plus 188 joules, plus I'm removing work, that is, I'm using it for work. So my work is going to be a negative number because it's decreasing the overall energy of my system. And so plus 188 plus a negative 141 is the same as 188 minus 141, right? And so that's going to give me a total of positive 47 joules. So in this scenario, I've added energy in the form of heat, and then I've lost some energy in the form of work. And so my overall is that I'm going to have a net effect of an additional 47 joules after I do that. So that's what that means. And then this one is for you. That was the example. And this is your for practice. And this was for you to use. And you're going to release heat. Sorry. Why I did that? Oops. You're going to release heat. And then you're going to perform work or does work on the surroundings. So you got to decide which one is positive and which one is negative, or they could both be positive or they could both be negative. So you work that one and see what you get. And in part 3, we're going to do some more calculations involving specific heat and heat capacity.